Welcome to Digital Logic Design. Throughout this tutorial, I'd like to request you to pause the video whenever you need it and keep pen and paper with you so that we can solve problems to consolidate our understanding. George Boole published a scheme for the algebraic description of processes involved in logical reasoning. The scheme was further developed and was known as Boolean Algebra. In the 1930s, Claude Shannon showed that Boolean algebra gives an effective meaning of describing a digital circuit built with switches. This algebra can be therefore used to describe logic circuits or logic networks. Like any algebra, Boolean algebra is based on a set of rules that are derived from a small number of basic assumptions. So these assumptions are called axioms. So let us assume that Boolean algebra involves elements or variables that take on one of the two values, 0 or 1. So we assume that the axioms shown here are true. So 0, so this dot operator is and this plus operator is or. So 0 and 0 is 0. 1 or 1 is equal to 1. So, and you have 1 and 1 is equal to 1, and 0 or 0 equal to 0. And if you do an AND operation between 0 and 1, it's always 0. But if you do an OR operation between 0 and 1, it's always 1. And if x is equal to 0, it's not or complement or inverse is equal to 1, and if this is equal to 1, then x naught is equal to 0. So these are not some things you have to memorize. So if you compare these things with ordinary algebra, you already know all these things. You already know that 0 times 0 is 0, so we don't actually have to memorize this. And the axioms in 4a and 4b are sort of the definition of NOT gate. So if the input is 0, the NOT gate is 1. If the input is 1, then output of NOT gate is 0. So these are pretty straightforward to remember. So from these axioms listed here, we can define some rules for dealing with single variables. So these rules are called single variable theorems. So let's say x is a variable, it's a binary variable. So x and 0 is equal to 0, and x or 1 is equal to 1. Again, x and 1 is equal to x, and x plus 0 or x or 0 is equal to x. So again, these are pretty straightforward because we can compare it with ordinary algebra and sort of remember this. So some of the more useful single variable theorems are listed below here. So x and x is equal to x. So when you AND something with itself, when you AND a variable with itself, then you end up with the same variable. Similarly, if you OR a variable with itself, you end up with the same variable. So okay, so x and x bar is equal to 0. So if x is 0 or 1, x bar will be 0 or x bar will be 1 or 0 respectively. So if one of them is 0, another one will be 1, which means 0 times 1 will be 0. And the exact same case here. So if x is 0, x and x bar, if one of them is 0, another one will be 1, which is why we end up with the expression 0 plus 1, and we know from axiom 3b here, 0 plus 1 is equal to 1, so you have 1 on the right hand side. And single variable theorem 9 is basically saying that if you double invert, or if you double complement a variable, you end up with the original variable. So the single variable theorems are very useful to remember, and from these lists, it's very clear that you didn't have to exert a lot of effort to remember this, because some of these are very obvious. So Yep, so we need to learn these single variable theorems. So we can prove these single variable theorems using axioms. So I've shown an illustration here. I'm trying to prove the single variable theorem 7a. So on the left hand, so if here we're trying to prove x and x is equal to x. So since x is a binary variable, it can take only two values, 0 or 1. So when x is 0, 0 and 0 is equal to 0. How do we get this? We get it from axiom 1a. So and 0 is equal to x, and we get the right hand side. Similarly, we can prove this identity or single variable theorem by just putting x equal to 1 and observing that left hand side is equal to the right hand side. So notice that we've listed the axioms and single variable theorems in pairs here. So this is done to reflect the important principle of duality. So given a logic expression, its dual is obtained by replacing all or operator or plus operators with a dot operator or and operator, and vice versa, and by replacing all zeros with 1. So see, we get 1b from 1a by replacing all zeros with 1 and by replacing all and operators with or operator. And in a similar manner, we get 1a as well from 1b. So the axioms and also the single variable theorems are listed by this relationship. So if you convert all the zeros into ones, and if you convert all the AND gates into OR gates, you end up with the other variable, or its dual version. So the dual of any true statement, be it an axiom or a single variable theorem, in Boolean algebra is also a true statement. Now you might wonder, why duality is a useful concept? So this concept will become clear later in the lecture when we show that duality implies that there are at least two different ways to express every logic function with Boolean algebra, and often one expression leads to a simpler physical implementation than the other, and is thus preferable. So duality also means you don't have to remember like all of these theorems. If you, let's say, forget that x plus 1 is equal to 1, but you remember that x and 0 is equal to 0, you can just dual this statement. So by dualing, I mean replacing the and with or, that is plus, replacing all the zeros with 1. Then you end up with 5b. So duality also gives us a way to easily remember the single variable theorems and the axioms. To enable us to deal with a number of variables, it is useful to define some 2 and 3 variable algebraic identities. So I've listed some of the 2 and 3 variable properties here. So for each property here, the dual version is also given. So the a and b's are the duals of each other. So you don't have to remember all of these because the 3 basic ones are commutative, associative, and distributive. These 3 are the basic ones, and the rest of them can be derived from the commutative, associative, and distributive properties, and also the single variable theorems and the axioms. So I'd like to suggest you to remember as many of these 2 or 3 variables as you can, but the absolute basics are the commutative, associative, and distributive. And you didn't have to actually memorize these things, because you can see commutative is x dot y is equal to y dot x, which means the order doesn't matter. So you can just reverse the direction here. So you can do x and y or y on x, you get the same result. And that's the same for OR. I think the most useful property is the distributive property, that you can sort of divide this x inside the variable, inside the variables that have been summed inside the brackets. So that's the main idea of distributive. So x dot y plus z is equal to x dot y plus x plus z, and that's the dual version of the distributive property. So distributive property, I'd like to say that is the most widely used property three variable property that we're going to see. But it's good to know commutative, associative, and distributive. But it's better if you know like most of these properties, if not all of them. But I think the absolute basics are commutative, associative, distributive, and also the De Morgan's theorem. So De Morgan's theorem basically is saying that if you AND two variables and to form a complement, it's exactly the same as ORing the complemented version of the two variables. So x dot y bar is equal to x bar plus y bar, and this is the dual version. So if you think it will be really burdensome, I'd like to request you to at least learn or remember 4 properties: commutative, associative, distributive, and De Morgan's theorem. But if you can do more, it's better. But as I'm going to show now, that we can prove the validity of these properties by using algebraic manipulation, like using the basic properties: commutative, associative, distributive, and De Morgan. So okay, so please pause this video and try to prove property 16b above using the single variable theorem and commutative, associative, distributive, or De Morgan's theorem, or any other property if you'd like. So please pause this video and then we'll match our answers. Okay, so hopefully you've been able to do this. So x dot x naught y can be broken down using distributive property, and x dot x naught is equal to 0, we know from the single variable theorem, and 0 plus x is equal to x. This is another single variable theorem, and then we end up with the right hand side. So all of these 2 or 3 variable properties can be proven using single variable theorems and commutative, associative, distributive properties. Okay, now please try to prove 13b and then we'll match our answers. So please pause this video. Okay, so hopefully you've been able to solve this. So again, we apply distributive property, and then we use the fact that x and x is equal to x, and then we again apply distributive property, and then we again apply the fact that 1 plus x is equal to 1, and then we end up with the right hand side. So you can try to prove some more of these properties using the single variable theorems, the axioms, and the commutative, associative, and distributive properties. Another way to sort of prove this, so the way of proving this that I just showed is called proving a logic expression using algebraic manipulation. So when you apply the single variable properties and 2 or 3 variable properties or axioms to prove a statement, it's called algebraic manipulation. But there is another way to prove this thing. So for instance, instead of applying algebraic manipulation, that is using axioms and theorems to prove a statement, what instead we can do is that we can plug in all possible input combinations and determine the left hand side and also determine the right hand side and check if that matches. So if we're trying to prove the De Morgan's theorem here, De Morgan's theorem has 2 variables, so it's a 2 variable theorem. So I've taken all possible combinations 0, 0, 0, 1, 1, 0, and 1, 1 here, and I have determined the left hand side of 15a, which is x and y whole naught, and I got 1, 1, 1, 0. Then I also determined the right hand side, x naught plus y naught, which is also 1, 1, 1, 0. So the left hand side is equal to the right hand side, which means I have proven De Morgan's theorem. So this is also another way to prove a property. Okay, now please pause this video and using axioms and 1, 2, or 3 variable properties prove the validity of this equation. So please pause this video and then we'll match our answers. So hopefully you've been able to solve this. So we start from the left hand side and we apply distributive property here to sort of break down the whole thing, and then we can apply sort of single variable properties x and x naught is equal to 0, and similarly x and x naught equal to 0. So then if we just apply commutative property, we end up with the right hand side. So this logic equation is valid. So here is another one. So please pause this video and try to solve this, and then we'll match your answers. So please pause this video. So hopefully you've been able to solve this. This is a huge equation here. So we have a huge expression on the left hand side and the right hand side. So what we did here is that we took both of them and tried to reduce them and see if the reduced version match. So versions match. So I've applied here basically commutative property, and then distributive property, and then basically single variable theorem that x plus x naught is equal to 1, and then I end up with this expression. And when we apply algebraic manipulation, we end up with the same equation on the right hand side. So the left hand side is equal to the right hand side, so the equation is valid. Okay, so thank you for your time. So if you have any questions, please let me know in the comment section. Thank you.